Hi physics students. Today we are going to learn about musical instruments and the different types of waves that are working with them in order to make the music. So a quick refresher from last week, a standing wave is a wave pattern that results when two identical waves travel in opposite directions and then interfere with each other. It's when the wave travels like that and then it hits something, reflects back, and it takes up this nice wave pattern, the standing wave. It has areas of nodes, that's where there's not very much movement, and it has areas of antinodes where there is a lot of motion of the molecules. When we're dealing with instruments, those molecules are either going to be air molecules like inside of an instrument when you blow into it, or it could be vibrations on a string if you are plucking a violin or a guitar or something like that. All right, two vocab terms to learn about. The first one is fundamental frequency. This is the lowest frequency of vibration for a standing wave. When you hear a note played, this is what the frequency that determines the note that you hear. It's what determines the pitch. So it's the first frequency that you hear, and then there is a harmonics or harmonic series. That is a series of frequencies or overtones that include the fundamental frequency and then multiples of it. And this is what gives the instrument or the musical note kind of its tone to it. All right, two different types of instruments. So we are going to start with stringed instruments and instruments that are open on both ends. Okay, so string instruments would be something like a guitar or a piano or a violin or a fiddle, anything like that. And then an instrument that is going to be open on both ends, an organ, you can open the pipes on both ends, or for us here in class, we're going to use boom whackers. The tubes that you hit against the table and they make a musical note. We'll also use that sound toy that you whip around your head, the dollar store toy. They are all open on both ends. In order for this to make a good note, a note that you hear, the wave has to end in a note. So either when you bang it and it makes vibrations, or when you pluck it or hit the string, in order for it to work, it has to end in a note. In order for you to hear good music, you know, sometimes you pluck a guitar and it doesn't quite sound right, it's because you haven't found a node. We have to have things end in a node in order for a good musical note to come out of it. All right, so as you look at these diagrams right here, we are going to look at the portion of a wavelength that ends in a node. So in a full wavelength, you go up and back down like this. A wavelength is when you start, when you get back to that same spot again. So this would be a full wavelength. So in a stringed instrument or open on both ends, the first time, if I were to then reflect and come back like that, the first time after the vibration occurs that you hit a node is right here, right there, and that would be equal to 1/2 of a wavelength. All right, we then continue on, and as you follow the wavelength right here, the next time you hit a node, you are at 1 wavelength. Then there's 1 and another 1/2, 1.5, and then 2 wavelengths, 2.5, and vice versa. So what's happening is in the scheme of a standing wave, every 1/2 of a wavelength, you have a node. So a reminder, a node, a node, a node. Here's the starting one. Here would be the first one, halfway through, then the second one, 1 full wavelength, and so forth. All right, so when we look at the equation, that helps us determine the fundamental frequency, what pitch that musical instrument is going to make. The equation has to include 1/2 of a wavelength. All right, so the equation, F of N, the frequency of the harmonic that you're looking for, is equal to N, the harmonic, times V over 2 times the length. All right, so when you look at these different, N is the harmonic number. So it's looking for, are you looking for the first harmonic, the second, the third, and fourth, or etc. And when you're solving for the fundamental frequency, which is what we do 95% of the time, this number is going to be a 1. The fundamental frequency, the first frequency of vibration, will be when N equals 1. So this will just be a 1, which means it won't affect the math that you're going to do. The frequency of the harmonic, that's what you're solving for, or that's the frequency that determines the pitch. The speed of sound, because this depends on temperature, is V, and then L is the length of the tube. So a standing wave for something that is stringed or open on both ends occurs every 1/2 of a wavelength, which is why there's the 2 right here. Think of this as 1/2, 1/2 of a wavelength, that's the L, is symbolized that it has to come into the equation. All right, for this, N can be a 1. You can have the fundamental frequency. It could be a 2. You could solve for the second harmonic, the 3, and vice versa. So you can put any number in for N. If you want to know the third harmonic, you would put a 3 here. But like I said, 95% of the time, we are going to solve for the fundamental frequency, which means N equals 1. All right, for our example, find the fundamental frequency for the spinning plastic tube that has a length of 0.8 meters if the speed of sound is 343 meters per second in the classroom. All right, so from up above, the frequency, we are looking for fundamental frequency, which means N is equal to 1. Okay, you could leave it out, times V over 2L. All right, so I am looking for the frequency of the first harmonic, the fundamental frequency. I'm just going to drop out the 1. The V is 343. I'm going to divide that by 2 times the length, 0.8. If I divide 343, this would be 1.6. Divide by that, I should find that the fundamental frequency is equal to about 214 hertz. The note that I hear played, then each note on the musical scale, as you start low and get high, it has its own number, its own fundamental frequency. That would match up. It could be middle C. It could be, it equals one of the musical notes. The question then is, at what frequency would the next harmonic occur? You can either put a 2 here and redo your calculations, or you can take the 214 and just multiply it by 2, and that would give you 428 hertz. There are decimals involved, they just round it to the nearest whole number. All right, so to find the next harmonic, a 2, you could put a 2 there, or you just multiply it by 2. Question, how does an instrument like a guitar with only a few strings play so many different notes? If you have seen somebody or have played the guitar, you'll notice that there's certain places that you put your fingers. When you hold it, you are holding it at a node. If you move your fingers or hold it in a different spot, you are setting up you're changing the wavelength of the string, the distance of the string, and by changing the wavelength, you're getting a whole new set of notes that you can hear. All right, so if you hold the string in a different spot, it changes the wavelength, which means you have a new fundamental frequency and harmonics. We got a whole new set of musical notes and pitches that you're going to hear. By touching in a different spot, you're changing the wavelength. All right, so for this specific type of instrument, anything stringed or anything open on both ends, we had a wavelength occur every a note occurs every 1/2 of a wavelength. So to find the frequency, you take N, the harmonic, usually a 1, and you multiply it by the speed of sound divided by 2 times the wavelength, because it's 1/2, the 2 goes on the bottom. All right, as we flip to the back side of our notes, we are gonna look at an instrument that is closed on one end. And once again, remember, I'm a terrible artist, but this is you. All right, you blowing into the instrument closes it on one end. All right, examples would be a trumpet, a clarinet, a recorder. If you had to play that in 4th grade, your recorder. Or when we're in the classroom, boom whacker. I'm just gonna abbreviate it, BW. A boom whacker with a cap. So I have caps that go on one end of it. By putting a cap on it, it'll make a whole different sound. And we're gonna see that in lab later this week. All right, in order for this to occur, because of how the air travels through it, in order for a musical note to be played, if you've ever blown into a recorder, sometimes you blow in and it doesn't really make a note. Other times when you have your fingers covering the right holes and the right wavelengths, then you do hear a note. And what ends up happening is, in order for a note to be played, this kind of instrument has to end in an antinode. It has to do with air pressure and getting the actual music, the air molecules to kind of move through the recorder or the instrument. It has to end in an antinode. Okay, think back. I'm going to draw a standing wave up here. Here's one wavelength like that. It then comes back. So this would be one wavelength. The first place you find an antinode is right here. On the scheme of the wavelength, this would be one wavelength. This is a half. That would be equal to 1/4 of a wavelength. Okay? So the first time we run into an antinode is at 1/4 of a wavelength. Okay? At 1/2, not an antinode. We are at a node. The next time we run into an antinode, we are at 3/4 of a wavelength. And then if we were to continue this out, here was 3/4, here's one wavelength, 1 1/4, which would be 5/4 of a wavelength. Notice we have a standing wave ending in an antinode is created every 1/4 of a wavelength, but not every 1/4, because there's not a 2. That's 2/4 would be 1/2, that's a node. Not 4/4, that doesn't work. It's only the odd numbers. Right? So for this kind of instrument to end in an antinode to get the musical note to play, it has to end, that only happens every odd 1/4 of a wavelength. Okay, so once again, when we get the equation, it has to factor into it. All right, equation starts the same. The frequency of the vibration, or the harmonic frequency, is equal to the harmonic. 95% of the time, that's going to be a 1. And then we are still going to have V. This time it's going to be 1/4 of a wavelength, so it's over 4L. But when we solve for it, we can't have N equal every number because only the odd ones end in an antinode. So you can have the first harmonic be a 1, but then the next harmonic will be a 3, and then a 5. Only odd harmonics occur for these type of instruments, okay? Because the evens end in a node and you don't get any good music to come out of that. All right, example number 2. What is the fundamental frequency of a 0.2 meter long organ pipe that is closed on one end when the speed of sound in the pipe is 352? So speed of sound, 352. The length is 0.2. I want to find the fundamental frequency, so that means I'm looking for all the ends are going to be equal to 1 times V over 4L. Because it is closed on one end, I just have to make sure I use the over 4L equation. Okay, plugging in my numbers, I'm just going to kind of drop out the 1s. I can just drop that out. The V, 352 over 4 times 0.2. If I take 352 divided by 0.8, I end up with approximately 440 hertz. All right. Fundamental frequency determines the pitch. This would be one of the higher notes for that. The question then is, at what frequency would the next harmonic occur? Okay, well, you can either change the equation to the next frequency of the next harmonic, or you can just take what you found for the first harmonic, 440. Our next harmonic, no evens. Have to skip a 2 because no music is going to get played there, and you have to go to the next odd, which is 3. So you would take 440, you would multiply it by 3, and you get 1320 hertz. All right, so the difference between the instruments is the other one, stringed or open, had to end in a node that occurred every 1/2 of a wavelength, whereas things that are closed on one end have to end in an antinode that occurs not every 1/4, but only on the odd 1/4 of a wavelength. So only odd harmonics will work for that. Thank you.